Welcome, everyone. I'm glad you're joining us here on the Saturday. We're going to kick off day 2 of the AMS Weatherband Jamposium. We're all here on a Saturday because we're passionate about the weather. Today's event is an opportunity to learn from experts, connect with others who share your passion, and be inspired to make a positive impact on the world. It's my pleasure to kick off our first webinar today. 2023 winter season won't soon be forgotten, with Jeff Halverson, Jamie Enderlin, moderated by Matt Vaughn, and with Greg Carbon joining us as a special guest. As we get started today, I would like to address some of the guidelines for our webinar. If you have questions during the webinar, please put them in the Q&A on the bottom of your screen. You can submit questions at any time during the webinar, and we'll get to them when we can. I'd like to introduce today's moderator, Matt Vaughn, who's an assistant professor at St. Cloud State University. And our speakers today are Jeff Halverson and Jamie Enderlin, and special guest Greg Carbon. Jeff Halverson is a professor of geography and environmental systems and associate dean of the graduate school at the University of Maryland, Baltimore County. Jamie Enderlin serves as the Chicago, Illinois Center Weather Service Unit's meteorologist in charge and is currently on a temporary detail to the NWS's Integrated Decision Support Services branch. Greg Carbon is Chief of Forecast Operations for NOAA's National Weather Service Weather Prediction Center in College Park, Maryland. I'd like to thank our whole panel for joining us today, and Matt, I'll hand it off to you. Thanks.
All right, thank you very much. And I'll share your sentiments that I thank again all of our panelists and experts for their time and expertise for us today. I'll start things off with Greg. This winter isn't one that we're going to forget anytime soon. And I understand that you have some graphics for us to show why this has been so unusual of a winter, particularly with regard to snowfall.
Yes, thanks, Matt. And it's an honor to be here today. I apologize for the late notice. It's been a busy couple of weeks, obviously, and but the topic is one that I wouldn't want to miss. So I appreciate you fitting me in at the last minute here. And in getting ready for today's talk, in just the last few minutes, I've been able to run some maps as a seasonal snowfall basically across the contiguous United States. Back to October 1, and then we'll look at the departure too and see that, who are the winners and the losers as far as the snowfall goes this winter. And then I'll pass off to Jamie, I think, and I know Jeff's got some really interesting information about some of the specific events, and we'll go from there. So let me see if I can share this graphic. Go full screen here, hopefully. So this is the season-to-date snowfall based on the National Weather Service hydro sensing unit out of Chanhassen, Minnesota. This is an estimate of snowfall, basically accumulated through February 25th, through the early this morning. And you can see where we've seen some belts of above normal snowfall activity. I'll toggle to the departure in a minute, but you get up to the reds, dark reds. You're talking 4 to 8 feet of accumulated snow. That's for the whole season, not necessarily on the ground at this time, but this is what they've seen. You can certainly see downwind of the Great Lakes where you're getting up to 10, 15, 20 feet for the season. In the west, the Rockies, especially the central Intermountain West, have done quite well. A couple of isolated pixels here up around maybe Steamboat Springs of 40 feet or more. And then the Sierra probably takes the prize. The mid part of the Sierra Nevada range in California, 40, probably 50 feet of snow in some isolated high elevation locations out there. And if we look at the departure here, I'll just toggle to the departure. And this is a departure from the 14-year average snowfall from 2008 to 2021, basically taking the same map as this for those years and then subtracting this from from that. And you can see where the winners and losers are. Certainly the Appalachians, even downwind of the Great Lakes, with the exception of these small isolated pockets near Buffalo and the Tug Hill Plateau downwind of Lake Ontario, almost the entire Northeast, well below normal snowfall, 2 to 3 feet below where they would normally expect to be, at least based on the past 14 years. Really well above normal snowfall in a swath here from northeastern Colorado across Nebraska, southern South Dakota into Minnesota, and especially northwest Wisconsin. This area here has seen a number of very significant snowfall events this past season, with storm track basically coming out of the southern central plains and then up into the Great Lakes, southeast Canada. In fact, some areas in here are probably seeing more snowfall than any other season they've had in the last 14, 15, perhaps even 20 years. And then we're just saturated at 3 feet or more of above normal snowfall across the Rockies and in Intermountain West, and then of course again in the Sierra. Interestingly enough, downwind of the Cascades, a little above normal activity here in northeast Washington, but for the Cascades as a whole, generally below normal snowfall, and the Northern Rockies as well, generally below normal snowfall, indicating perhaps the storm track, the very moist Pacific air, coming in a little bit further south than where you might normally expect it up here in the Pacific Northwest. So we've got an event ongoing in Southern California that's certainly going to add to the positive anomalies down here, with heavy snow falling this morning across parts of higher terrain in Southern California. In fact, not all that high terrain. The snow levels in Southern California are very low. Unusually so, and blizzard warnings in effect for the first time in decades, perhaps across parts of the mountains of Southern California. So winter continues. Go back to the total snowfall through this morning. And we're going to see, we'll see changes to this map, of course, and we may even see some hope for these below normal areas along the East Coast. It's kind of fitting that it's been snowing here in the Mid-Atlantic DC area this morning as we start this conversation. So I'm going to pass it back. I'll stop sharing here. And again, appreciate you allowing me to join on such short notice this morning.
Thank you very much, Greg, for sharing that with us. And you can really get a picture of how this winter's been through those graphics. Really below normal on the eastern side of the country, with the exception of those areas just downwind of the Great Lakes, and then quite high positive anomalies out in the west. So winter weather has a lot of wide-ranging impacts, and one of those impacted sectors would be aviation. And I'm sure you've all seen the headlines for this winter that aviation certainly had quite a bit of disruptions here over this past winter. So we have Jamie here from Central Weather Service Unit. She's the meteorologist in charge. Jamie, I want to pass it off to you. Just tell us a little bit about what the Central Weather Service Unit's mission is and what you've really noticed about this winter season at your office.
Will do. Let me pull up my slides really quick.
Well, Jamie, I think you might need to unmute yourself.
Matt, it got me. When I started sharing, it muted me. Thanks.
All right, there you go.
Okay, starting over. For those who don't know what the Center Weather Service Unit are, we're weather service employees who are embedded in all of the FAA air traffic control centers across the US. There's 21 different centers. So I'm here in Chicago. We are weather service employees providing everyday weather support to air traffic controllers directly in their facilities, so we can work together to keep the flying public safe. Kyle Struckman created these slides I'm going to present. He's the acting meteorologist in charge of the National Aviation Meteorologist. So essentially same job as mine, but they're at the FAA Control Center out in Virginia, where they're looking at the whole country. So we collaborate together from locally to the FAA Control Center nationally to just route airplanes across the US. Again, the name of the game is safety and just informing the FAA with what we're seeing. So that's a little bit about what we do. And this is just, I'm going to go over a general picture of winter and then a few events as well. So Greg already covered this for me, which is fantastic. He did a better job than I was going to do. It's been typical in La Nina year. Greg showed you where we had snow. We don't have snow. Again, here in Chicago, I come from a family of snowplowers, and I don't see any snow on the ground. So I'm getting an earful from that locally. But the one thing that every winter, of course, for aviation, we do have to deal with is an increase in icing. I just saw Kansas City Center yesterday had some icing concerns with we have moisture in the air, it's colder, so there's always a possibility of icing on aircraft. And then also as the jet stream sinks further south into the CONUS, into the continental United States, and it's a strong jet stream, we can have increased periods of severe turbulence as well. Here in the Midwest, we've had that for a few weeks now. So I don't have any slides on that, just some common winter aviation hazards we have to worry about, just increase in icing and then moderate to severe turbulence. But winter weather specifically, going to start out with the recent event this week in Minneapolis with the winter storm they had up there. So between February 21st and 23rd, Minneapolis, the airport received 13.4 inches of snow. That was the second largest February snow that they've had on record. And actually, if you look at all Minneapolis snowfall events, this was the 23rd highest one. And as Kyle put together here, on the 22nd, February 22nd in particular, Minneapolis airport operations were 66% below normal. So a little bit over half, pretty significant, especially when you consider it's Minneapolis. They do see quite a bit of snow usually in the winter, but having, again, 13.4 inches of snow in total took a toll on airport operations. One good thing about, in general, with winter storm systems is we see them coming. We can talk to the FAA and the airlines and communicate. We see the snow coming. It's going to be more than what we usually see. And then the airlines and the FAA can be a bit more proactive with how are they going to handle operations, just to make sure we have flow of people and planes being safe and efficient. So in this case, there was probably a lot of cancellations. The next event was the Dallas-Fort Worth ice storm, January 30th, February 1st. So Dallas metro area had up to a half inch of ice. The airport itself also had 1.3 inches of snow, which was a new daily snowfall record for January 31st. And ice, completely different animal than snow. So I want you to think about when you go outside, if you've ever had snow on your car and you go to clean your car, if you have a 1.3 inches of snow, you brush it off and you're good to go. Hopefully the roads are plowed and you can continue on. If you have a half inch of ice though encasing your car, that's a whole different story about how to get that ice off. It's going to take you a lot longer. And just because now you've uncrusted your car, let's say, the roads are still covered, everything's covered in ice, as you can see in the picture here on the right that Dallas-Fort Worth actually tweeted out. All the equipment's covered, all parts of the airplane have ice just hanging off of them. And then that's just the ground. Now, when you get up into the atmosphere, you're already looking at possibility of some icing accumulating on the aircraft, which causes all sorts of issues. So this is a much more big impact event than just snow. And as you can see at the numbers Kyle put together, on February 1st, Dallas-Fort Worth was 86% below normal. So very significant event. Here in Chicago, we actually, the person who's second in charge of the facility I work at, he was stuck in Fort Worth for a few days because of the ice storm. So I just found that ironic that an FAA person also was stuck somewhere because of inclement weather. And finally, while you may not think thunderstorms are a winter phenomenon, as Greg showed in the South, especially just lack of precipitation and snow, but we had a bunch of thunderstorms. And thunderstorms are, we're getting back into that season, and it's always an interesting time of year with aircraft operations and thunderstorms. So in this picture that Kyle put in from January 4th, you can see pretty much a solid line of thunderstorms extending across Georgia through the panhandle of Florida and the Gulf of Mexico. So in this case, unlike a winter storm, it's more of a reaction to the thunderstorms that occur. We can forecast you're going to have thunderstorms today. That's what we think is going to happen. But in general, with aviation operations, we want to see where are they forming? Is it a solid line? Are there breaks that we can fly through? Is it more scattered? In this case, it's a solid line. So as you can see, we don't have percentages of lower operations because the FAA and airlines handle thunderstorms differently. In this case, there's a ground stop at Atlanta. So it's basically saying thunderstorms are getting to the airport. We're going to stop all traffic in and out of the airport until they pass, and we can safely start resuming operations. And then how do we get around these storms? Again, they're not flying pretty much through that line of storms. So it says there's an airspace flow program for Jacksonville Center. Basically, how do we move aircraft around all these thunderstorms? So it's a much more tactical approach. Still trying to, I mean, we deal with thunderstorms year round, but there's been uptick in them in this winter. In fact, I was looking at, for Chicago on January 19th, we actually had a plane struck by lightning. The only lightning bolt we had that day happened to hit aircraft. Everyone's fine. There were no issues. But even up here in Chicago, thunderstorms and gusty winds have been more impactful than snow this winter. So that is what I have.
Great, thank you, Jamie. I just want to ask you one quick question. When you're in this tactical scenario between, well, essentially as thunderstorms are ongoing, how important is it for you as meteorologists to try and get the storm mode right between that cellular type convection versus, say, a line of convection that day of?
It's very important. We very much speak in terms of coverage. Actually, we have a collaborative forecast. We work on the entire convective season of just that. Where do we have confidence in the coverage of thunderstorms? So I joke, actually a squall line like we saw, or like a line of storms, is a lot easier for us to work with the FAA because they can see it coming, they can route around it. A more air mass scattered pop-up thunderstorms is a nightmare scenario for aviation because it's not moving. And you can't really route, airplanes usually move like highways in the sky. But if you've got pockets of thunderstorms all over the place, you can't route thunderstorms around them. So it's much more, there's less of a plan. It's more of everything's changing every 5 to 10 minutes. So the mode and the coverage are what we really focus on, and how tall are the thunderstorms as well.
And speaking about how tall, Jamie, I was just noticing here, it looks like we're looking at maximum echo top heights, and I see 56,000 near Tallahassee, Florida.
Mhm.
Now that if that's true, that is truly remarkable for this time of year anywhere in the continental US.
Yeah, and a rule of thumb we like to use, anything over 32,000 feet, aircraft can't fly over. So that's when we start hitting 32, of course, when you get closer to an airport, that threshold lowers, but anything over 32 and it's, well, you're going around.
So are you also trying to forecast, say, the overshooting top height for these thunderstorms as well? Or are you just trying to look at, say, where that top height on the radar is?
I would say both, especially, like I said, when tops get closer to actual terminals, like Atlanta in this case, we're looking at tops to see whether we think pilots are even going to want to fly through them. When you talk about overshooting tops, those are interesting because when you have that overhang, sometimes pilots will see that and think, I don't want to fly through that. That looks dangerous to me, which is valid. So we try to forecast, here's where actually the thunderstorms are located. You may have overshooting tops extending hundreds of miles away, and pilots may just say, I don't want to fly there because that looks like a scary cloud. Again, completely valid. We even have cases of thunderstorms hundreds of miles to the south, but they're causing severe turbulence up in the Chicagoland area. So thunderstorms just bring a whole slew of aviation hazards with them.
I wanted to comment briefly on the tops there. I noticed that high top too, Jeff, down there, 56,000. I don't think this has been peer reviewed, but I remember early in my career when we used top forecasting as a proxy for potential wind gusts at the surface. So a 56,000 foot top, you might get up around a 56 knot gust. But you know, I mean, we know that probably doesn't apply, but for a quick rule of thumb, that's something I remember from early in my career.
I never heard that one before. That's really interesting. I like that.
Me neither. We're all learning something on a Saturday morning or early afternoon.
Excellent. Well, speaking of thunder, I understand that there may have been some thunder in perhaps a little bit of an unexpected place this winter, a little bit closer to Buffalo. Now, if everyone would recall the snowfall anomaly or departure from normal maps that Greg showed, there was a very localized maximum downwind of Lakes Erie and Ontario. And a lot of that was caused by a singular event, the Buffalo lake effect snow event. And I believe Jeff has some additional information on that to take us through what happened during that event, what made it so devastating.
Yes, thank you. So I'd like to go ahead and do some sharing here. Let me just get set up really quick. All right, folks. Well, we're going to look a little bit at a outlier event for relatively early in the winter, the days leading up to the Christmas weekend. I think Christmas was on Sunday, and so Thursday, Friday, the week before, this meteorological monster, what we call a bomb cyclone. Bomb cyclone is a storm that's a very rapid deepener. And we say 24 millibars in 24 hours or exceeding that. We did a lot of coverage of this on the Capital Weather Gang back at the time. So let's go ahead and talk a little bit about this. Seem to have lost my cursor. There we go. So these big storms, we think of them in terms of superlatives when they become historic events. The satellite image you see here, very high resolution of the storm when it was in its most intense state. You see that enormous comma head. And there are at times hurricane force wind gusts sweeping across the surface beneath that comma head. Snow falling at the rate of 2-3 inches an hour, thunder snow, extremely impressive system. And so, well, it's being called a once in a generation storm. Even I've heard storm of the century referred to by folks in the greater Buffalo area. But this was also tied to a major Arctic air outbreak, one of the big ones we had this past winter. So Greg Carbon is really, really great at coming up with analogs. And he wasted no time when we started chatting this morning, say, hey, Jeff, 1978 Cleveland superbomb. Similar in a lot of ways. So these are not unknown systems. As a matter of fact, November is when typically we get very, very strong cyclones over the Great Lakes. They're called November witches. The Edmund Fitzgerald was sunk in 1975 by one of those extreme cyclones going across the lakes. A very hazardous part of the country, particularly in the fall, early winter, when some of the lakes have not yet frozen over, and some of that lake warmth and moisture can really, really contribute to the intensity of these big storms. So as far as I could find, about 100 fatalities, which is a horrific number of folks from a winter storm. And this is over 20 states in the CONUS and 2 Canadian provinces. The interesting thing here, about 37.5 consecutive hours of blizzard conditions across Buffalo. And it was truly, truly, truly a life-threatening situation for anyone that was venturing outdoors. And as I said, these hurricane force peak wind gusts, and I'll show a figure in a little bit that presents a time series of that, but upwards 79, 80 miles an hour across parts of New York. And then, of course, we have to throw in Mount Washington in New Hampshire being at, well, I guess, I'm not sure, maybe 4,000 feet elevation, something like that. 151 miles an hour. Mount Washington has lots of superlatives racked up for it this past winter. MCP, that stands for minimum central pressure. This storm rapidly deepened from about 1,001 down to 963 millibars. That's a very, very low pressure over the center of North America. We can see pressures like that not too uncommonly over the winter oceans. But to see this over land is truly, truly impressive. Max snowfall. So this is where I'm a little confused, and I'm glad you're here, Greg, because I found the 57-inch total at Snyder, New York from the WPC report. But I know there's been discussion of 70 inches. Greg, do you have any information on where that 70 inches occurred?
My guess is that it wasn't near Buffalo. I think the higher amounts for this were probably downwind of Ontario. I could be mistaken, but if I remember the analysis map afterward, I think there were higher amounts over like the Tug Hill Plateau, Montague County, New York. That might be where that is.
Okay, thanks. $5.5 billion damage, 7.5 million power outages. That is an extreme total for a singular event. The last time I've seen outage figures that high for anywhere in North America, well, that would be Hurricane Irene in 2017 across Florida, Georgia, and the 2012 June 29th derecho, Ohio Mid-Atlantic derecho. Those are comparable numbers. And to see this come in a winter event is truly, truly astounding. And then, of course, a nod to Jamie here, 18,000 canceled flights, which is an atrocious number in the days leading up to Christmas. So this is just horrible timing, folks. So, the superlatives go on and on, but here's the cold air anomaly tied to the formation of this storm. These big cyclonic storms, folks, get their energy from air mass temperature contrast. The gradient in temperature is a reservoir of potential energy that is, when you lift the warm air and you sink the cold air, you generate kinetic energy in the system in the form of swirling wind. So you've got this tremendous mass of Arctic air with anomalies of minus 30 Fahrenheit against norms for this time of year, just being funneled down to the east of the Rockies. Tremendously strong high pressure cell, advecting, which means moving horizontally, these extreme cold temperatures. And now look up over Hudson Bay and some of the northeastern Canadian provinces well above average anomalies. So you take the warm anomalies up here, the bone chilling anomalies here, you've got one heck of a temperature gradient to sustain a very, very powerful cyclone. This just gives you a taste of, when you see a map with all these colors, it's going to be a bad weather day for someone. And your eyes instantly go to the reds and the pinks, the reds. And this is the day before the storm as it was getting organized. All this is blizzard in the red here. And, we see parts very close to Chicago getting in on blizzard warnings. Here's Buffalo getting its blizzard warning. And the pink is winter storm warnings. And up over New England, there's high wind warnings. So this just gives you the extent of the wind field of this enormous storm as it started to come together. Now, this is a busy map. This is my infamous take the surface charts and tile them and try to show the sequence of the developing cyclone. What we're looking at is a series of 4 surface analysis charts starting 7 p.m. December 22nd. Then we move down to 7 a.m. December 23rd, then zip up here to 7 p.m. December 23rd, and then finally we end on 7 a.m. December 24th. So a 48-hour period. And this just shows the evolution of the cyclone. And on the evening of the 22nd, all the ingredients are in place. Look at this Arctic air mass. You've got a surface pressure of 1,052 millibars. And just to put that in perspective, anytime you see an air mass in the 1,040s this time of year, it's a very, very strong high pressure and very, very cold air. But when you get up into the 1050s, that is a very uncommon type of value. And you see this cold air just spilling all the way down into the Gulf of Mexico. And along this frontal boundary, which represents the thermal contrast, we have the genesis of the storm center here, 1,001 millibars over southern Michigan. Well, look what happens over the next 12 hours. I mean, there's one closed isobar around this storm. And now look 12 hours later, how many closed isobars? This is what's called bombogenesis. This is the barometer just crashing as this system just really, really, really takes off. Now we're down to 982 millibars. We go 12 hours later and the storm is at 970 and then reaches its minimum pressure 12 hours later, 963 millibars. The other thing I want you to notice is if you compare 7 a.m. December 23rd, 7 p.m. December 24th, 7 a.m. December 24th, this storm has barely moved. It's crawled very, very slowly to the north over that 36-hour period. And that, to see something like that, means a long duration event. That's just hour after hour after hour of unremitting high wind, wind damage, heavy snow accumulation, extreme wind chill. 37.5 hours of blizzard conditions is partly due to the large size of this system and its very, very slow movement off towards the north. So I take you up to jet stream level because this is really where storms are generated. Everything that happens at the surface can be traced back to something that's going on at jet stream level. And this is an analysis from the Storm Prediction Center. The morning of the 23rd, as this storm was really starting to take off over Western New York. The big feature here, and I know Jamie's really used to looking at these jet stream charts, a howling polar jet stream, the core of which is looped into this enormous trough. And this is a trough is an area where you have counterclockwise rotation of winds within the jet stream and a core of extremely cold air. So I've indicated the axis of the trough for you here. This is what we call a negative tilt trough. And what that means is it's in a highly amplified state with a tremendous amount of curvature, tight gradients and spin energy. And it's hard to see in this diagram, this white arrow. I've tried to highlight the core of the jet stream. This is the core of fastest winds. We call this a jet streak. And this is the type of thing that gets Jamie really nervous because when you get into the boundaries of these jet streaks, you get a lot of wind shear, clear turbulence, which is hazardous to aircraft. And also the headwinds are not favorable for aircraft flying towards the west. They burn a lot more fuel. But in the meteorological setting of the storm, this black X indicates a very important location. When the air flows out of this core of high wind, it experiences a lot of uplift. And so we call it the left exit region of a jet streak. A lot of rising air here. And also you see spreading apart of streamlines shown by the red arrows like a fan shaped spreading of air. That also contributes to uplift. So it's kind of a chimney effect, like the atmosphere is ventilating the surface and causing air to rise very vigorously. And that's one major factor that contributed to the rapid intensification of this big cyclone over Buffalo. So you had not just a wicked temperature gradient providing the energy, but the jet stream was really stoking this system as well. Okay, this is a really neat graphic. This also comes from the Storm Prediction Center. Up here at the very top, you see the core of the lowest pressure, 963 millibars. And what we've drawn here are isobars, contours of pressure, every single millibar. And when you start to look at a big storm and you're looking at every millibar, then you really start to appreciate what we call the pressure gradient, which is the change in pressure over distance. Anytime you see lots of isobars crowded together like this, the gradient is huge, which means the acceleration of air at the surface is enormous. So look at the breadth of this wind field. This is just a simply enormous wind field. And I want to highlight something here. This magenta box, I've got this circumscribing Lake Erie. And what you'll see if you look very carefully at this and you know what to look for, you see the little vector arrows show the direction from which the wind is blowing and the speed of the winds. And the thing I want to highlight here is the winds accelerating at the surface. This is a surface map, accelerating over the surface of the lake, speeding up, and the winds are perfectly aligned with the long axis of Lake Erie. What that means is when you have a long fetch like that, you have the maximum time for those winds to extract heat and moisture out of the lake surface, thus destabilizing the atmosphere and priming the lower atmosphere for convective lake effect clouds. And so the lake effect, even though this storm was exiting to the north and the pressure was rising across Buffalo, the lake effect endured for many more hours just by virtue of the low temperature of this air mass and the extreme winds aligned perfectly with the axis of the lake. And I think this is my final figure here. This is from the National Weather Service office in Buffalo. This is what we call a time series. So what we do is we take selected variables that are measured automatically at the surface, and we chart those as a function of time. Okay, so the colors indicate the different things that are being measured from the 23rd of December through the 24th of December to the 25th of December, 48-hour period here. And the blue line, the blue trace, indicates the sustained wind. This is probably the 1 minute average wind. And it shows that for a time, the winds were sustained at tropical storm force, which is above 39 miles an hour, particularly early in the storm as it was rapidly intensifying. The black dots indicate instantaneous values of peak wind gusts. So these are the peak wind gusts. And at the early phase of the storm, the first 24 hours over Buffalo, a lot of these gusts were getting over 60 miles an hour. Some were approaching 70, if not reaching 70 miles an hour. And then the green indicates the direction of the wind. The prevailing wind direction throughout this event was from the southwest, as you just saw on my previous slide. So you see this sustained period of extreme high wind. It's snowing at a wicked rate. And so we go down to the bottom panel, which really tells the story of the blizzard. This is the visibility in I think statute miles, or maybe nautical miles, might be statute miles. Anyway, the visibility just crashes to zero at the onset of the storm with the high winds and the snowfall, and it stays at zero for nearly 40 hours. So when you have zero visibility, folks, you are in a blizzard. And so this is the meteorological proof in the pudding of that fabulous event that was unfolding there. Okay, so I think we're going to stop there for now. That's just a very, very basic overview of this very historic storm. Perhaps the panelists want to mention certain things at this point. We'll go ahead and stop sharing.
Yeah, thank you, Jeff. Before we get the other panelists in on this, I wanted to just quickly ask, why don't we typically see these bombs over land? You highlighted the intense temperature contrast that we had there. Why is it so often that we see these over the ocean, but so rarely over the land?
Well, it's a lot of people have studied this, and Greg, certainly welcome your comments here, but a lot of it I think has to do with the availability of ocean heat. It turns out that these big wintertime ocean storms are kind of hybrid cyclones. Yes, the temperature contrasts are very important. The jet stream is important, but when those storms incubate over, let's say, the Gulf Stream with very, very high warmth and a lot of humidity, it turns out that a significant amount of the storm intensity comes from extraction of heat from the ocean. So the low layers of the storm are almost behaving like hurricanes in some sense, but I'll leave it there and switch over to Greg and see if he has anything to add.
Oh, there's so many things. It's fascinating when the atmosphere does some things that are so extreme. The Midwest is not it's not necessarily in the winter months unable to generate these intense temperature gradients near the surface. So, the bomb cyclone that Jeff just talked about, not much different than what you might get with the intense gradient that develops along the East Coast and the warmer maritime air mass of the Western Atlantic. That system basically had the same ingredients in terms of the temperature differential, because the air coming out of Canada was so remarkably cold that you didn't really need to warm up all that much ahead of it to still sustain an incredible temperature gradient between the Midwest and the East. Unfortunately, the East has been on the warm side of a lot of these systems this winter. And one really kind of interesting aspect of that particular cyclone, Jeff, that I noticed, there was a little pocket of above normal air when I think it was the last map, which was either Christmas Eve day. Most of your map has temperatures well below normal because the low pressure system's all the way up near James Bay in Canada. But there was one pocket of above normal temperatures, and for above normal, I mean around freezing, that happened to exist right up near James Bay. And that warm air pocket got pulled into that system and wrapped all the way around it. And it was just a small anomaly up near James Bay where they got up above freezing. And that just gives you some idea of how that system just mixed up the atmosphere in an incredible way. And yeah, those gradients. The other thing I noticed about the Lake Erie low level winds is you could see the winds coming together across the lake
Mhm.
too. So they weren't just flying, the same direction. They were coming together, resulting in convergence in the low levels. And basically that vacuum effect, the chimney effect you talked about being realized right over the warm Great Lakes. Just incredible what the atmosphere can do when given the right conditions like that and the right ingredients.
Yeah, and I'll also add that, we can't neglect the presence of the lakes as well as a potential energy source. The lakes collectively behave like an inland sea.
Right. Yeah.
And they contain, the warmth, the vapor, that's all energy for a big storm. And when the winds start cranking at the surface over those lakes, they're called fluxes. You start drawing literally the warmth and the moisture out. That air gets enriched with that energy, and that feeds right into the system.
And the
It could be
deepening,
15% of the intensity of that storm probably could be ascribed to the presence of that lake heat source.
Real quick, as we're talking about the season, I happened to notice the other day that Great Lake ice coverage is actually at some of the lowest levels it's
Mhm.
been since records began. And it's remarkable that it is this low, given that we've had a number of Arctic outbreaks. The problem is they just haven't persisted over the lakes. They've been 1 or 2 days of very anomalously low temperatures, but then you're back to normal or above normal. And across all of the Great Lakes, the ice cover is well below normal for this time of year.
Good point. Good point.
And Jeff, if I may, you mentioned with the jet stream, of course, turbulence. So while you were speaking, I looked up some of Cleveland Center covers the Buffalo area, some of their forecasts. They did have forecasted moderate turbulence higher up in the atmosphere, but what I thought was interesting was the severe turbulence was actually, they had at or below 18,000 feet and then at or below 6,000 feet. So I just pulled up some old soundings, and sure enough, like you said, while the winds at the surface were out of the southwest, just a kilometer above the surface, it was out of the southwest at 25 knots. So just that turning in the low levels was potentially causing some severe turbulence. So these things bring a myriad of fun, if you
Yeah,
will.
you're talking about literally the whole troposphere generating extreme levels of turbulence in a situation like that. That's a very unusual situation. Yeah.
Yes.
Yeah, Jamie, I just wanted to ask, for an event like this, say in the Detroit airspace, when you have such a wide wind field, is there a concern about runways having, say, too much crosswind over them, and then you start to, say, delay air traffic there? What are the types of things that are hazards for a Central Weather Service unit outside of just kind of the icing and the turbulence?
Right. So it depends on the airport and how the runways are configured. So I'll use O'Hare's a pretty easy example. It's mainly an east-west airport with east-west runways. So we get really gusty, which we've had this winter, strong south winds. It reaches a threshold where that crosswind becomes an issue where it's too much crosswind to either take off or land. Sometimes it's up to pilots if they feel comfortable. Add in any sort of precipitation that causes wet runways, and you've now lowered that threshold to how much they can handle as well. So it's a little bit of, we have actually, due to some internal studies, a rough guide on where those thresholds are. But when you add in, it's still up to the pilots. They of course get to declare what they think is safe. And then you add any sort of reduction of friction on the runways, and then it becomes a bit more difficult. So that's another one we try to give a heads up, but it may be event by event, how do we handle it type thing.
All right, well, it looks like we have a couple of questions coming into the chat, and I think one of these pertains to what we were chatting about earlier here. About one attendee asks, any thoughts on the remainder of the winter season into this early spring? There appears to be some shift in the pattern recently with some upper level troughing in the Northeast and a possible shift to a negative NAO. And similar to that, looks like we're also shifting into a pattern that's supporting more Colorado lows, particularly with this big event that swept across the upper Midwest and plains. Any ideas on what may have driven this change in the pattern?
Greg, I
Who's
think
gonna
you're
bite that one?
a good person to answer that.
So it looked to me that, Jamie's schematic of the La Nina flow regime is not really that different from what we've seen. It might be displaced perhaps just a little bit south. In other words, above normal, instead of the Pacific Northwest, we're seeing it down across central California. So overall, that schematic seems to match pretty well with the La Nina. Now we do know though that the La Nina has been fading somewhat. It's not a strong La Nina by any means, and in fact, maybe headed toward neutral, and then an El Nino warming of the Pacific later this year. And that has implications that I don't even want to start to think about. Who knows what the storm patterns will look like, or what the temperature anomalies will look like going into an El Nino, which we haven't seen in a few years. So overall, I would say that that the variability of that flow regime has a lot of aspects to it, and ENSO is just one part. Day-to-day variability in the jet stream. These strong systems are not necessarily uncommon during the winter months when you see these strong temperature gradients that we've seen. It's definitely been an interesting winter, much above normal in the east, below normal temperatures for the west and north central. And every winter is going to have its anomalies, right? So is just a small part of that.
But I do note it is kind of interesting that we've been in a La Nina for 3 years consecutively. Now how many, Greg?
I think it's 3 so far.
3. Yeah, which is really interesting. Really interesting.
One other point, when I saw another question in there about the anomaly of below normal snowfall in the east, and the impacts from that. What's interesting, I did some work answering a question about this about a month ago. Snow drought actually is different than regular rain drought, right? And when you think about it, you can have a snow drought, but not necessarily a drought. And what we've seen in the east, especially along the eastern seaboard from DC to Maine or Boston, the precipitation has been above normal, but falling in the form of rain as opposed to snow. So while you're in a snow drought, you're not in a precipitation drought across some of those areas. Although if you go just inland, I was just looking at the 90-day departure from normal. Basically from the central Appalachians, just inland from I-95, there's a swath there where they're reporting below normal precipitation. So snow and liquid slightly below normal for the past few months.
Yeah, speaking of the differences in snowpack, particularly in the east, I believe the West Coast may have a little bit more snowpack, particularly in California, due to a series of atmospheric river events that have impacted that area. Jeff, I know you had a little bit on the California systems. Perhaps you'd like to share that and speak about what this does to the reservoirs there and on the West Coast.
Yeah, I can go ahead and do that really quick, because I know we're coming towards the end, and also there may be a couple additional questions. But to get kind of cut to the chase here, we're talking about the last 2 weeks in December, first couple weeks in January, an unprecedented number of the so-called atmospheric river events. And these are just some pictures from AP, from Washington Post, that indicate the extent of damage. So not just, and I'll define what an atmospheric river is in a minute, but very, very powerful storms coming in off of the Gulf of Alaska and hammering most of California for weeks on end. So you can see the wave damage here, the undermining of roads along the shoreline. The amount of damage here was just mind-boggling. But it's really the delivery of fresh water was extreme for this area. And you see here, utilities suffering a lot of damage because of landslides. Mudslides, debris flows coming down, taking power lines on slope terrain with them. So I want to show this map, and I know these are the kind of maps that Greg is fond of talking about. This looks at the selected precipitation totals, and we're also talking water equivalent when you talk about snow. So we convert the snow to liquid, And then we try to look at the total precipitation. And so I believe Marty Ralph mentioned to me at least nine successive storms over that multi-week period, maybe additional ones. And those storms containing so-called atmospheric rivers. But your eye goes to the pink colors here. This is Sierra Nevada, right? And so these are very high elevations. Now, I'm not sure where the snow line was in these storms, Greg, what altitude that was at, but above a certain level, it's heavy, wet snow, and 300 to 4 inches of snow from that 4-week period were some of the amounts I was looking at. But here we're talking, rain totals 30 plus 35 inches, et cetera, along a fairly significant portion of California. Also, you see the coastal mountains picking up a lot of that heavy rain as well. And this is the interesting slide here. Since about the year 2000, large area of the American Southwest has been in what's commonly termed a mega drought, which is multi-decadal period of drought conditions. And to the point where before these storms, we had a big piece of California in severe and even extreme drought conditions. You've seen the pictures, folks, of reservoir levels, the bathtub rings on the banks of the reservoirs where the water had once been, just really, really sobering low levels. And then this is the after these rivers, the drought is essentially erased for this part of California. Now, we don't know how durable that's going to be, right? Because this is a drought prone area. When we go back and look at climate studies, we see records of these mega droughts going back thousands of years when you do paleoclimate studies in the region. So the area is very, very prone, but having a generous amount of snowpack in the mountains is always a blessing for the coming summer, the coming warm season. And the fact that some of those reservoirs recovered to almost the pre-drought values was astounding. So I just want to finish up by saying this was the prevailing jet stream pattern throughout those 4 weeks, with the core of the jet probably a little further south than what's depicted here, but really persistent troughiness and storminess and a series of cyclones coming in. And there's a satellite image of one of the cyclones. And then on the southern end of the cyclone is where we have the so-called atmospheric river. And so this is a diagram that shows the moisture anomaly. This is for, I can see the date here. I think it's mid-January. One of the big storms, you can see the cyclonic calm ahead of the storm, but this area of blue is very, very high atmospheric water. It's called precipitable water. And this is percentage above normal for this day and this location. And you're running precipitable water anomalies 250% above what's typical. And the source of this water is in the subtropics, if not tropics. And this is the so-called atmospheric river. Atmospheric rivers are not liquid water, but they are, you can think of them as 200, 300 mile wide ribbons of high and deep water vapor content, saturated air coming out of the tropics and being focused and aimed by these cyclonic storms right into the orography. And then essentially you have upslope flow, orographic uplift on the west-facing mountain slopes in the Sierra Nevada, the Cascades. All that moisture condenses out, freezes out. And this is just, it's a moisture delivery conveyor belt that feeds right into a lot of California. So I'll go ahead and pause there. Any of the panelists want to say, but that's just the briefest of overviews of what's happened out there in the West.
Yeah, I was going to mention the depiction that you had of the broad jet stream structure didn't appear to be the typical La Nina pattern, which tends to have the jet stream a little bit further to the north. Do you know if the La Nina index was a little bit lower during that time, or what may have caused that?
I've wondered about that too. It did seem like an anomalous position for the jet, given a typical La Nina, but I don't think there's any such thing as a so-called typical La Nina. La Ninas have a lot of variation. They each have their own personalities. And I think, Greg said, that this jet was riding a bit further to the south than we typically expect to see. But that's a good point, Matthew. I don't know if the index had relaxed. That would be a fabulous thing to look at.
Yeah, I just think there's a lot of variability in these systems as they move in from the Eastern Pacific. However, if you look at some of the historic atmospheric river events in California and some of the high-end daily precipitation totals, it's not at all atypical to get these events in late December, early January. 2017 was the last year, and it kind of, I think, Jeff, it did the same thing with the drought. It flipped the drought in 2017 in a matter of a few weeks. And I looked at the events of this year, and for I think it was January 10th, that was the third wettest December, January, February day over the state of California, if just sum up the gridded precipitation. The first wettest was a January 5th, 2008, and then a January 9th, 2017. So that early part of January, typically we'll see these events unfold across the state of California. And just for trivia buffs, estimate about 32 trillion gallons of water fell on California with these events through early January. That's, I think, about the it's almost the entire volume of Lake Tahoe, which is a huge deep lake, and I think it's a third of Lake Erie dumped out over California in a matter of 2 weeks period of time. So that's some trivia, weather trivia for you.
Well, excellent. It looks like we're just about wrapping up here. So I'd love to thank our panelists again for their time and expertise here. We've all had a fascinating discussion about the different events that have taken place during this winter that really is one that's not soon to be forgotten. So thanks again to the panelists, and I'll go ahead and turn it back over here.
Well, thanks so much, Matt, and thank you to Jeff, Jamie, and Greg for everything today. For those of you coming partway through the session, all Jamposium sessions are going to be available to Weatherband members at amsweatherband.org. If you have any further questions at this point or want to talk about the webinar, members are welcome to discuss on the Weatherband Community Forum. I'd like to thank you all for joining us today, and you can join us for the U.S. Top 10 Weather Events at 1:15 p.m. Eastern. You can join the session using the link we've just put in the chat. Otherwise, I want to thank you all so much for joining us. This is an excellent discussion. Hope you have a great rest of your day.